Get ready for the Speed of the Game podcast from downtown Detroit with your host, Dan Gilbert. If you can't keep up with the speed of the game, well, you can't play.
Welcome to another episode of the Speed of the Game podcast. I'm Dan Gilbert, and we're here in downtown Detroit as usual. You can see it behind us, and you can see, well, you sort of can see a little water over there. Across the water is the Great White North, Canada, and that's going to be relevant in just a minute because we have a very special guest here with us today and a very special show. And this is Dr. to my right here, Dr. Shohini Ghose, who is the professor of physics and computer science with a focus on quantum physics. And she is tied to many universities, but specifically tied to Wilfrid Laurier University in Waterloo, Ontario, Canada. Do I have it right?
Yes.
We practiced that for about 6 months, and then I finally still kind of messed it up.
Got it perfect.
But I got to tell you something. I'm so excited that you came here to Detroit, and you know I saw Dr. Shohini Ghose on a TED Talk, and you have a few of those, right?
I do.
And you know I sort of have it as a hobby, this quantum physics. You know, I'm a very dangerous amateur, just know a little bit. But quantum physics is so just incredible and so counterintuitive and so everything. You've been studying it since the 1990s?
Oh, yeah. Ever since, actually, undergrad days is when I first really encountered it. And then I loved it so much that I decided that in grad school, that's what I'm going to study. And since then, I've been fascinated and often confused by it.
Yeah, as everybody has since Einstein's days, right?
Yeah. Oh, yeah.
It's, quantum physics is a bizarre thing, and we could probably talk here for hundreds of hours, sitting here going. We got you for about another 18 or 19 minutes, and so we're gonna do quantum physics for dummies, which definitely includes me on this subject. And I got to tell you, I saw your TED Talk, and the way you described it prompted me to say, let's go find her and get her to Detroit, not just for the podcast, but to talk about quantum physics in general. But is it possible to give somebody or the audience a 60-second primer? This is quantum physics.
Wow. I'll try.
58 seconds left.
Okay, so here we go. So quantum physics is the theory that we use to describe the behavior of microscopic particles, the fundamental particles of the universe, such as electrons, for example, or photons, which are particles of light. And the theory that we use to describe them is kind of strange because it predicts that these particles can behave in strange ways that we in our macroscopic world don't really experience. So for example, there is something called superposition. So an electron could be in combinations of locations.
But let's stop right there because I'm sure the audience understands that. You're not saying different electrons. You're saying the same electron. Yeah. An electron has mass, so it's a thing, right?
Oh, yeah.
So the same thing can be in more than one spot at the same time.
Well, that's what our description of it at least is. So there is some likelihood that it exists in one location and some other likelihood that it's in a different location. Where it actually is, we will only know after we observe it, which is kind of weird. Does it even exist before that? We don't know.
So when you take that theory to its end, right, it's like, does the world, when I turn over here, does it exist until I look at it, right? Is that really when you take it to its ends?
It could be. We don't really have a good understanding of this. What's the meaning of it all? We can certainly write down accurate equations. And from that, we can calculate these probabilities. But before we observe what is actually happening, who knows? That's what makes it weird.
It sort of goes back to that tree falls in the forest thing, right?
Right?
Is there a sound or not kind of thing?
For sure. This is the quantum version of it.
So tell me if this is right. Albert Einstein at a very famous conference tried to prove quantum physics to be not true, or at least a part of it.
Yep.
And he came up with the concept that the math was telling him that entanglement, this thing called entanglement, works. And if that works, something's really wrong with your theory. Therefore, it doesn't work. But it turns out that entanglement, which I would like you to describe, is actually a real thing also. Is that right? Did I have that right?
Yeah. So, in fact, yes, Einstein wrote this paper back, in the 1920s or 30s, I believe. And this paper is famous. It's called the Epr Paper, named after Einstein, Podolsky, and Rosen, who are the three authors. And in this paper, his goal was to prove that this quantum theory predicts very strange things. One of these strange things is entanglement, which I'll try to explain in a minute. And his conclusion was that because of these very strange predictions of quantum theory, there must be something wrong with the theory.
Yep.
And in fact, this Epr paper is now Einstein's most widely cited paper, more than relativity or anything else he ever did. And he was pretty famous, so this is something.
So let me get this right. So he actually wrote a paper to disprove, what was the other guy, the other Swedish, or the
Niels Bohr.
Niels Bohr, is that right? Was he from Sweden? Is that, or Switzerland? I don't know which one, but
Danish.
Okay, I'm sorry. Neither. So so basically, he wrote this paper because they had this big sort of feud going about quantum physics, and he wrote it to sort of disprove what Niels Bohr was doing or saying, or his theories, and it ends up being his most famous paper ever.
Right. So it's, it was a friendly feud.
Yeah.
It's not like they hated each other. In fact, they had great respect for each other, which is why they had this ongoing debate. And back at that time, we didn't have, of course, the technology to go and observe these kinds of effects that entanglement would produce. So these were all thought experiments. So Einstein would be like, imagine if there were two particles, one in location A and one in location B, and you measured this, and so on. So they tried to dream up these experiments, which is what Einstein did in the paper, and said, well, if you went and did that experiment, you'd find this weird thing where somehow one particle instantly knows about the properties of the other. Measuring one will give you information about the other.
So that's entanglement.
That's entanglement.
So go ahead and give a layman's view, or not view, but description of what entanglement is, because this is the weirdest of all, right?
Yeah. So the thing about entanglement is, imagine that you have a single particle at location A and another particle at location B. What's weird about entanglement is that individually we don't precisely know the full identity of the particle, meaning exactly its location and its direction of motion, for example. Right, its speed. So it's almost like if you had a GPS where you could either see on your map where you are, or you could read what your speed is, right? But you couldn't do both, right?
Okay.
That's the weirdness of quantum theory, where you have this uncertainty. Entanglement is even weirder. It says that you can have two particles where each of them, of course, has this uncertainty built in, but the real information about the two of the particles is not in the individual locations. It's in the joint information about the two. So if you know the position of one, you know exactly the position of the other. Or if you know the speed of one, you know exactly the speed of the other, no matter how far away in the universe they are. So they're always connected, but the only real identity they have is together.
So the particles, did they have to be attached or touching each other at one point first, or is it any two particles?
Yes, no, they have to be interacting at some point in the past, then after that they don't interact, but they can have this connection. So
just to try to tell me if this. So you have two particles that are somehow connected to each other. You separate them. Yeah. I put one over here, let's say right here on this desk.
Yeah.
I put the other one on Pluto.
Yeah.
Or a planet off of Alpha Centauri, or in Waterloo, or in Cleveland. Okay, and I turn one clockwise. The other one goes counterclockwise at the same time, faster than the speed of light. Is that?
Well, typically you don't really, you can do operations to one locally. That will not change the other. But when you observe, remember that the thing about quantum that is so weird is that there's always uncertainty. So you don't exactly know whether your particle is, in a particular state or not until you observe. And once you know exactly what one particle is, you know exactly what the other one is, no matter where it is in the universe.
So would it be I observe one as heads, the two coins, the other one is automatically tails?
Yeah, exactly.
And
no matter what.
At the same moment, without them even, they can measure, right, speed of light. They're entangled with some other force that we don't know.
So it's pretty weird.
Which is why Albert Einstein said spooky action at a distance,
For sure, yes.
He said there can't be spooky action at a distance, or it is spooky action at a distance.
He had many interesting quotes. He also said God does not play dice, because he's talking about this randomness.
With the universe, right? So, man, oh man, so now we're going down the rabbit hole. I feel it's going deeper and deeper. So, but there are companies and even governments right now, correct me if I'm wrong, that are basing this entire theory of quantum computing on quantum physics and entanglement, right?
Yep.
And if they keep going down the road they are, the way somebody wants to describe it to me is that we will have computers that aren't just like double the fastest speed today and can do double the amount of calculations, but it's like millions of times, something crazy. It's like comparing today's computers to people maybe exchanging a couple stones for a couple sheep or whatever it is, right? Mm-hmm. Is that an accurate way if you take it to its conclusion?
To some extent. So one thing, though, to be careful of is that we don't know whether a quantum computer can solve every problem today faster than a classical computer. It can certainly do as well as anything we have today once we build it. Mm-hmm. But it doesn't mean that in every case, for example, doing email is not going to get better, unfortunately, because we use a quantum computer.
Nothing in the universe could solve that problem, right? Really? There's nothing that can solve email.
Not even Einstein.
No, not Einstein, not quantum physics, because the email is going to kill us all eventually. Always. Man, somebody's got to solve it.
Unfortunately, that's the bad news. However, there are some very important problems that we already know of where we don't know of any existing way for a regular computer that we have today, even a supercomputer, to be able to solve, but a quantum computer could do it. So one of the most important examples is actually just factoring large numbers, finding the factors. So 2 times 3 equals 6, that kind of problem. It may not sound very interesting, but if you take a really large number.
It sounds horrible. That's like, who wants to do it?
But they're doing that for important.
But they're doing that for a reason. What is the practical outcome of that? Why do people do that?
Because in fact, all of our current encryption is based on the idea that factoring is actually a very hard problem. Meaning if I take a 100-digit number and I ask you, what are the factors? Turns out it's a really hard problem.
But why do I care about the factors of a large number? I don't even care about large numbers. Like, why do I?
Because
why does anybody care about the factors?
You're using it all the time because since it's a hard problem, if somebody wants to hack into your encrypted information, they would have to know how to factor the large number. Now, even our supercomputers today can't really do anything more than a few hundred digits. And this is an open question.
Yeah.
And people are working on this all the time, try to find better and better ways to factor. Okay. Turns out a quantum computer has a particular way of doing this using entanglement that would be able to hack into our current encryption in minutes.
So is part of it, I'm just gonna sort of like, I don't know what I'm gonna do. If you have one computer sending something to our quantum computer over here, sending something to quantum computer over here, mm-hmm. If it's a regular computer, people can hack in along the way, right? Is that accurate? I mean, they can sort of, in their fiber, however they're communicating in mm-hmm. the air, wherever it is.
Yeah. But
we're saying is the computer is quantum is just because certain information here, certain information here, so there's no delivery of there's no in the classical sense. Is that what makes it more secure too? Because they can't.
Right. So there's 2 pieces to this. One is the current encryption we have is no longer going to be secure once we have a quantum computer. So then we have to ask, we need a better way of encrypting, right? Yep. How can we do that? Turns out quantum physics comes to the rescue. Okay. So we can create new ways of encryption that has nothing to do with factoring, thank goodness, that will be completely secure. And the reason for that security is that it's not based on just how hard a math problem is, like factoring. It's based on the laws of physics. So anybody who wants to hack into the new quantum encryption would have to break the laws of physics, which hopefully we can't do.
Putting your name on the line which is dotted at the bottom of a mortgage document for your first mortgage, or even your second, third, fourth, or fifth, doesn't really matter. That's a big financial obligation, and that's a big commitment. Probably the biggest financial commitment in your life. In fact, the average person makes no larger commitment than paying back a $100,000, $200,000, or $300,000 home loan, or even higher. So you want to make sure that you go to the best company you possibly can go to. Well, there's one company that has risen from nowhere, really, in downtown Detroit, Michigan, they're headquartered, to become the #1 home lender in America. More people trust Quicken Loans and Rocket Mortgage for their home loan than any of the other 30,000 or so companies that are out there. So why did that happen? Well, this company cares deeply about you and client service. That's why J.D. Power ranked them the best experience in home lending for the last, 9 consecutive years in a row. And on top of all that, they have the best technology. I'm sure you've seen the commercials. It's called Rocket Mortgage. Rocket Mortgage, press button, get mortgage. Now it sounds real simple, and it is for the user or the borrower or the client when they're looking at it, but this is years in the making. Thousands of technology people and others creating the best and quickest technology that has interfaces to all the sources to verify things quickly. So you can get a home loan not only quick, but you can get it in a visible, clear, transparent manner. So if If you're thinking about a home loan or you're thinking about buying a home, you want to go to rocketmortgage.com, or you want to download the app on iOS or Android. So Rocket Mortgage, America's largest lender and the best lender. But although quantum computing to the classical physicist is just kind of crazy stuff, is there still
to everybody?
Is there still debate like within the physicist community? You get Physicist Today magazine. What magazine do you get? What is it called?
Well, there is a famous magazine, Physics Today.
It is Physics. Will you guys subscribe to that one, please, for me? Is there another one? Is there like Physics Monthly? Is there Physics Yearly? No.
Oh, that's a good question. Well, there's a lot of very technical physics journals. Those are the ones I tend to read, unfortunately.
Oh, so like Entanglement Tomorrow or something. Like is that one? No.
Not something that's non-technical, unfortunately. No. But
One
Scientific American will sometimes carry stories about.
I actually get that one. You get New Scientist.
I don't.
It's a really good one. It's like twice a week. Comes out of Britain.
There's also Physics World.
Physics World's big.
Yep.
I get that one too. Please. Okay. Don't worry, we have it in the budget. You guys are all worried. Okay, I'm just kidding you.
We have one in Canada called Physics in Canada. So.
Oh, there's not how much it can be going on. No, now that's crazy because we just had a conversation before we went on the air that Canada has the leading computer or quantum computing company, D-Wave, I guess, one of the leaders,
yeah.
And a couple others. And was the government involved or something? There, some reason maybe it's so cold over there, that you guys. By the way, Detroit is the only place in the whole United States. We're north of Canada.
I was told that, yes.
Isn't that crazy? You got to go south to Canada over here. Just the way that piece of land comes around.
So you're effectively Canadian.
Yeah, I mean, the sort of, what do they call that? De facto, I guess, de facto.
Yeah. Honorary.
So, I don't even know what my question. Now I'm all messed up here. We're talking about why does Canada have so much going on? It's just cold, you're bored, and you're doing, so tell us.
Well, Canada's got a history in this because this idea that we can do cool things with quantum weirdness actually started with Canadian involvement. So there were these two scientists, Gilbert, who's based in McGill University in Canada, and Charles Bennett, who was at IBM at the time, who got together and wrote this paper describing how you can actually build this unhackable encryption by exploiting this weird thing called quantum uncertainty.
Right.
And that was in 1984.
So it's embraced the weirdness.
Yes, and that led to, basically more and more of this kind of research in Canada.
And we all know that Canadians have been embracing weirdness for a long time.
We're just weird.
Sorry, guys, I'm just kidding. But got a lot of people actually to come across the river here, either the tunnel or the bridge, and work here. Canadians.
I know,
we opened up an office over there in Windsor.
That's great.
So let's sort of switch to another topic. So a big part of quantum physics and the theory is something called Schrodinger's cat, right? There's a physicist, right? Another famous. What was his name?
Erwin Schrodinger.
What was his first name?
Erwin.
People call it Erwin. Just
yes.
Okay. Erwin Schrodinger. And I'm going to set it up, and you're going to tell us how it works. But basically, if there's a cat in a box, and there's something going on with radiation, you'll tell us. The cat is both dead and alive at the same time. So give it that one. I've had a hard problem understanding.
So like Einstein, Schrodinger actually was trying to show that quantum theory gives such weird predictions, like dead and alive cats, that there must be something wrong with it. So this was yet another attempt to prove quantum theory somehow being flawed.
So the way to become a really famous physicist is to try to attack somebody else's theory with some other thing, and that theory that you're doing it becomes the main thing.
We just like to be right, so we'll prove everybody else wrong, right?
Gotcha.
Something like this. So the idea is that there's some kind of a radioactive atomic sample in this box with the cat.
So wait, let me for us lay people. So we have a box that we're going to put a cat in that's alive when we put him in?
Well, okay, yeah, let's assume
Let's say he's alive when we put him in. We put some radioactive pebbles in there.
Sure, some kind of material, which is can be described in quantum terms because it's an atom.
Okay.
That's the quantum piece there.
And then we shut the box.
We do. We close the box. Now, the thing is, the radioactive substance can decay because it's radioactive.
Yeah.
And when it does, it triggers a poison in the box.
Okay.
And because of that, the cat will die. So the question is, will the poison get triggered or not? Now, the point is that because we're talking about an atom, which should be described with the quantum theory, it can be in this superposition of decaying and not decaying.
So just to describe superposition, That means that's what we talked about earlier. That's the electron, the single electron that has a possibilities of being here, 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 and here.
Exactly.
And until a human being looks at it, it doesn't collapse into one reality.
Right. So the same thing applies to this atom in the box.
Yep.
It has some possibility of decaying and some possibility that it doesn't decay. And it's sort of before you look in the box, you don't know. So before looking, your description is that the atom is in some combination of decay and non-decay. That's the superposition.
Okay.
But we know that this means that that means the poison is being triggered and not triggered, because it's that combination.
Yep.
And that means that the cat is in the superposition of dead and alive. And that's too weird. And Schrodinger's point was, well, obviously no cat is dead and alive at the same time, so obviously there's something wrong with the theory.
And it turns out that he was right. The cat is dead and alive at the same time.
Exactly.
Until you look at well, if he's dead, until you look at it.
Yeah.
Once you look at it, then when you see that it's dead or alive, that reality collapses into one. Is that what? That
was it exactly. So Schrodinger too was, unintentionally wrong in thinking that there was something wrong with quantum. So far, this is the most well-tested theory we have, both in experiment and in theory, and we have never found a violation of its predictions.
Entanglement is what you're...
Yes.
Yeah, okay, so, and they're doing a lot of this in China, yes?
Yep, and all around the world, actually.
And you told us that China's really made a bet on quantum.
Mm-hmm, absolutely.
I mean, so if you're like the President of the United States or the Secretary of Defense or whatever, I mean, that's something that, I'm not saying I can even conceive of the manifestations of that. But if a country like China got light years ahead of, let's say, the United States in that kind of thing, I mean, we could be creating black holes and things that, wormholes and things that maybe, we gotta catch up a little bit. Do you think United States, Canada, do we have to catch up at this point?
Sure. I'm Canadian, so I don't really know exactly how the policy works here in the U.S.
No, don't worry, we don't know either, so don't worry about it.
But for sure, China is well ahead of the game in the sense that they've invested heavily in this, and they're building world-class quantum research labs. They've also launched a satellite whose sole purpose is to implement quantum communication technologies that would lay the groundwork for maybe a global quantum communications system. Wow. However, I will also say that a lot of this work, yes, at the national level, there's probably some kind of a quantum race and competition going on, but at the research level, there's also collaboration.
Yeah, so that's good. I think we'll all be better off as a world. Everybody collaborates on this stuff.
And often when we make discoveries, of course, we publish them, and these are openly available.
Yeah. I read something, we don't have to get off on this tangent, but that Einstein, when he published certain things early in his career, that because he didn't maybe go to one of the top universities or one of those things, that they weren't taking him as serious, and then finally they started taking him more seriously. Is that accurate? Do you?
I'm not sure about the history of it. I do know that he came up with several of his very fundamental theories, including relativity, and also the start of quantum theory, when he was working as a patent clerk. He wasn't even at a university.
Because I don't think he could get into the ones that were
the
ones his dad wanted him to go or something like that.
So after those papers were published, he did get an offer. So I'm guessing that they did get noticed.
Is he? If you were to meet somebody, you could have dinner with any physicist, anybody in science. Let's say 3 people who are connected. They don't have to be quantum necessarily, but connected to science, dead or alive. Like the Schrodinger's way, it could be dead or alive. Who would they be? The 3 scientists, guys, people.
I'd say Marie Curie. Of course, because she was an incredible scientist back in the day when it wasn't common.
So is this the 1920s? When was
Even
she
before
around?
that. So she won her first Nobel Prize. She won 2. Her first Nobel Prize, I believe, was in 1911, or maybe that was even her second one. Well, early 1900s is what we're saying. She was incredible because she was a wonderful scientist and, one of the only women in the field at the time. And
I'm surprised that those guys, the way they were acting back then, let her in the first place. Did she have to overcome a lot of things?
Well, she and her, she was actually doing her work along with her husband, Pierre Curie. Mm-hmm. And in fact, they were, when the Nobel Prize committee actually awarded the Nobel Prize, they actually only awarded Pierre, her husband.
And she done all the work. She did the work.
She was the leader of that experiment. And he actually stood up for her and insisted that they include her. And that's how she got.
good.
Her second Nobel, she won all on her own. So
And then just a few years later, she won her own.
Yeah,
That's good.
So, but she did face a lot of challenges as a woman back then.
I can't even imagine. So that's one. Who are the other two?
I guess I would say Einstein, of course.
Of
Who
course.
wouldn't want to meet him, right? I think
No.
he was either a time traveler or an alien. He was so far ahead of his time.
I would ask him about his haircut at first. That would be my first. Like, if he was on the show right now, that'd be my first thing. We break it down. I'd say, okay, Albert, like what's going on?
Yeah, I'm trying, but it's not
yours
the
is
same.
great. No. And how about number 3?
Number 3, are we talking still scientists or
Well,
physicists?
yeah. I mean, I'll maybe accept the third. We'll give you some latitude. So.
I'll have to think about that. I was also always inspired by not just science fact, but science fiction because it's so creative and imaginative.
So you're going to go with like Kirk or McCoy or
I'm
Spock?
going to go with Isaac Asimov, who wrote a lot of science fiction.
Oh, he was the writer for all
Yeah,
that. Okay.
and in fact, his ideas are, just basically, if you look at all the current movies, many of those ideas came from his work. So.
Well, you actually mentioned to me in the office before we came out here about teleportation, which was in Star Trek when they beam me up,
right?
Scotty. So how does quantum physics potentially create that for us?
So we're definitely not at Star Trek level teleportation. What we're talking about is teleportation of information. So zeros and ones, a message of some sort.
Yeah.
But it's teleportation in the sense that if you want to send the message from A to B, you don't have to physically send it on a wire or a piece of paper or whatever, right?
Because of entanglement.
Exactly. So you use entanglement between, your sender and your receiver in such a way that all you have to send to the receiver is a set of instructions saying, dial in these sort of settings on your device, and the message will appear on that side. So anybody who's trying to hack wouldn't even have anything to hack because the message is not being physically transmitted.
Yeah, that's what I was trying to say earlier. If you have 2 points,
Yes.
because of entanglement, without getting into the real deep details of it, bottom line is it doesn't go through any space to get there, right?
It's quite amazing.
That's just
isn't it?
it's the craziest thing. So what normally again, I would almost vie for a extra special bonus hour with you, but we'll do that another time because our guys, we all got to run. But I'm going to ask you one last question because this is always, I know I stay up thinking about this a lot. Like, you can describe almost anything in the universe. You can describe sort of space, at least, describe what it is. You can describe what shirt I'm wearing, what headphones and all that. But what really is time? And we all know time is not a clock. That's just moving, what is time itself?
That's a great question. I don't know if I can answer it in
Or
2
does
minutes
it, or does
less.
it exist?
Again, a great question, and I don't think we can, have a definite answer right now. I can tell you my ideas around it.
Takes too much time. You know what I'm
For
saying?
example.
No pun intended.
So many scientists will tell you that time is related to this idea that we call entropy. And entropy is this idea that the world is becoming, or the universe is becoming more disordered, right? From order to disorder,
So
actually.
shit is the default option.
Yes,
what
unfortunately.
you're saying.
That's where we're all heading.
Things left alone, you pull down, it's going to just decay and
Exactly.
okay.
Yeah. So it's sort of the standard example is like, if you take an egg and you make a fried egg, you can't like unfry it and go backwards, right? So entropy increases, and the direction of that is what we call the arrow of time in one direction.
Okay.
It gets really interesting at the quantum level though, because in quantum theory we know how to describe entropy in terms of information. If you increase in entropy, this disorder idea is the same as losing information.
Yeah.
Right? So actually the arrow of time therefore means loss of information.
So
which is
all
quite
time
amazing.
is loss of information. So
Knowing
the
less
more,
and less.
The more time we that goes by,
The less you know.
So that's why people say the less I know, there's more
There you go.
complication. That
We are all deep quantum
Yeah.
philosophers.
because it really is you can't really, like, I always wonder, like, what makes now. I mean, it was 10 minutes ago. It will be 10 minutes from now. I can't really. How do I describe what now is? Like,
There
how
is no
did
now.
Yeah.
Right?
Or maybe there's only now.
Or
No?
now is already past before.
Well, it just did. Just
Exactly.
really quickly. So on that note, hey, first of all, I cannot thank you enough for flying here from the north in Canada.
Thank you
You
for
didn't
having
swim
me.
across the river, did you? You flew here. And if you didn't remember her name, it's Dr. Shohini Ghose, professor of physics and computer science, the focus on quantum physics, and she is associated with the Wilfrid Laurier University, Waterloo, Ontario, Canada. Will you come back?
Of course,
Dude,
anytime, and you should
wait.
come visit us.
Oh, we'll come visit you for sure. We're coming there. You know, it's Waterloo. They got a lot going on in science, technology, not just quantum physics, right?
No, it's a huge startup culture there and lots of tech.
It's sort of a little bit of a secret in the United States here. We should know more about it because, you know, it just, you know, they got computer science, like you said, and engineers, and those are the people that.
Sure. There's
that
also
are
a lot of
big
AI
demand.
stuff.
Oh, artificial intelligence. We'll get to that on the second time.
All right.
So, hey, thank you for coming, and everybody, you know, from Detroit, Michigan, thank you for watching the Speed of the Game podcast. This is another episode. It's not another, what do we call it? What? Edition. It's not an edition. Edition's a paper thing, like a magazine, right? Is that the difference? Yeah. This was an episode. So, anyway, remember, you gotta keep up with the speed of the game, or you can't play. Good night.